And a lot of people had questions about the quiz you guys took last week, mostly about this problem where you have to like estimate. I should start. Let me pin my video before I get going here. People had questions about how to estimate the partial derivative with respect to x or y when you're given this graph of level curves. So the idea here is that, right, when you're trying to find fx, you're really trying to find, in fact, I think what he did in class kind of talks about this. You're basically trying to find the change in your function divided by the change in x. That's what fx is. And if we're approximating fx, we're just going to look at this to see. So the change in your function is the change in the z values, or the change in the level curve values. So if we're trying to find the partial derivative with respect to x at the point 1, 3, here's how we're going to estimate that. We're going to look at the point 1, 3. We see that, okay, at the point 1, 3, we have a function value that looks like it's about 14, because it's on the level curve 14. And then to estimate, so we have to have some change though. So what I'm going to do is I'm going to move in the positive x direction. Sorry, this is the x-axis. This is the y-axis. I'm going to move in the positive x direction to another point that's kind of easy to read. So I'm not going to go just over 1 because I don't really know what the function value is there. I'm going to go over to this next point where it looks like my level curve is kind of perfectly cutting the point 3, 3. So I say, okay, I can see that f of 3, 3 looks like it's 16. So then I can say that the change in f divided by the change in x, well, the change in f is 16 minus 14. The change in x is 3 minus 1, which ends up being 2 over 2, which is 1. So at that point right there, it looks like the partial derivative with respect to x is approximately 1. And this is an approximation. To find the partial derivative with respect to y, we would do the same thing, except we look in the y direction. So at this point, if I move up to, say, the next convenient point, which looks to be right there, I can say that my delta f over delta y appears to be, well, from here to here, delta f is going down to, right? It's going to be, you can do it as, right, 12 minus 14, right, where you end up minus where you start, divided by the change in y is going to be, well, let's see, let's say we're from here to here. That looks like it's at 6, so the change in y is going to be 6 minus 3. So it looks like my partial derivative with respect to y is approximately negative 2/3. Okay, let's do a couple more just to make sure we're really. Also, he did say there was going to be something like this on your test, right? Estimating the partial derivative using the level curve. So it's good practice. For fx at 3, 5. So at 3, 5, we're at this point here. My example, no, that's fine. So at that point here, to move in the x direction, usually you move to the right, but you could also, like, say if I move back, like, what's the difference in the difference? That would also work. I'm going to move over to this point here, which my graph is not perfectly drawn. Okay, looks like it's about, let's see. It looks like I went up 2 for my function. And it looks like my x value increased from 3 to 6. So that's going to be 2/3. And then it looks like fy at the same point at 3, 5. If I go up to the next value, I'm going, my function value is decreasing by 2, and my y value seems to be increasing by 2. So that's how we can kind of estimate a partial derivative using a level curve graph. By saying, okay, how much is the function changing? And the function is the level curve values divided by how much is the variable that we're taking the derivative with respect to changing. And that's kind of how I would say, okay, I move over to this other point, my variable increased by this much. Just to kind of show you, like, I wanted to graph this thing, kind of show what it looks like. Right, here's kind of what the graph would look like. So you can see that, like, for example, at the point, 1, 3. So like I'm up here somewhere on the surface. Sorry, I'm up here at 1, 3, we were pretty high at 14, right? Didn't have that on my, didn't draw that one, sorry. So over here at 1, 3, right? We're like right here, and we're asking, okay, what happens when you move? I think I drew the graph wrong. I'm sorry. I was trying to draw it right, but I definitely think I drew it wrong. Here's how I know why. If I draw this so that I'm moving in the x direction, I'm moving down, and that's not what should be happening. If you move in the x direction, you should have a positive rate of change. So I definitely drew this wrong. I was doing it kind of fast. Yeah. Oh yeah, I see. It should be higher up the further out. So it should actually be kind of like flipped front to back. So like this back part should actually be what's over here, and this front part should be kind of facing back that way. So then if you move that way, you would be going up instead of going down, right? Sorry. Okay. It's not really the point. It's having 3D graph anyway. So I want to address that one, and I think most of the questions people have is about that. Oh, I suppose let's talk about the domain and range one also, because people definitely had questions about the domain. Let me start more about the range, although the domain as well. So various people for question 1 had some sort of function that looked like e to the pick your favorite negative number times x squared plus y squared. I think everybody had some version of that. Yeah, I'm going over just a couple problems from the quiz because people asked about that. That reminds me, there was also someone had that question. Cool. And then we're going to get into directional derivatives. So for this one, the domain. For the domain, I don't see any of the 3 indicators that there's any issue. There's no square roots. There's no division by 0. There's no what's the other thing? Logarithms. You might, and you would be not incorrect to say, well, James, technically you could have maybe division by 0. You would not be wrong. If you think about this as 1 over e to the positive 8 times x squared plus y squared, then you can be like, hey, James, you could be divided by 0, right? There's division. And I say, you're right, but there isn't, because e to any power is always greater than 0. So no domain issues. Domain is all points x, y in the plane. Okay, the range is a little bit harder to deal with. And it might actually be made easier by writing it like this. So let's talk about the range. So here's what I know so far. I know that x squared plus y squared is bigger than or equal to 0 and is less than infinity. Okay. And then I'm going to try and make it look like that. So I'm going to multiply everything by 8. Doesn't really change either of those things. 8 times 0 is still 0. 8 times infinity is still infinity. Right? Now my pens, I really need, I'm supposed to get some new pens, but they haven't come in yet. So my pens are getting kind of out of black ink refills. I have to start using red and green, which just don't show up quite as nice. So anyway, I'm going to do e to the each of these things. E to the 0 is less than or equal to e to the 8 times x squared plus y squared is less than e to the infinity. E to the 0 is 1. E to the 8 is what we want, right? And e to the infinity is still infinity. Finally, I'm going to do the reciprocal of everything. The reciprocal of 1 is 1. But when I do the reciprocal, I change the direction of the inequality. 1 over e to the 8 times x squared plus y squared. And then the reciprocal of infinity, 1 over infinity, goes to 0. So it looks like my range here appears to be 0 exclusive to 1 inclusive. We can't get 0, but we can get 1. So it's actually a pretty small range. Interesting. And then if you were going to graph the level curves, sorry, let's go ahead and do some red, why not? If you're going to graph the level curves, you would, at least I would, I think you would too, you would take this equation, set it equal to z star is what he likes to use, right? Or e, or c is also fine. but 1 over e to the 8 times x squared plus y squared equals z star, reciprocal both sides, e to the 8 times x squared plus y squared equals, oh, actually, I should explain, what am I doing? I see x squared plus y squared, so I'm trying to isolate the x squared plus y squared because I'm pretty sure I got some kind of circle. A natural log of both sides. So 8 times x squared plus y squared equals the natural log of 1 over z star. And then divide both sides by 8. So x squared plus y squared equals 1 over 8 times the natural log of 1 over z star. So this tells me that my level curves are circles centered at the origin, and the radius is the square root of whatever this number happens to be when you pick a value for z star. A value for z star that's in the range. So for example, if we pick, say, z star equal to, I don't know, let's make something, I don't know, 1/4, then we get the equation x squared plus y squared equal to 1/8 times the natural log of 1 over 1/4, which is just 4. So this would be a circle with a center of 0, 0, and a radius that's the square root of 1/8 times natural log of 4, which is not a nice number, but it is a number. So yeah, level curves. So really, I don't remember exactly what the quiz question said, but if you were to describe the level curves would be circles of varying radii, and I don't believe they're equally spaced out because you've got a natural log of 1 over z, which means you're going to need some weird spacing. Okay, that's most all I have to say about the quiz, unless there are any other questions about the quiz. All right, so let's talk more. Oh, I looked at the graph of the function f worth and it looked relatively even. Oh, okay. Maybe the, it might just be because there's such a small range that might be why they look evenly spaced, Max. I'm pretty certain they're not evenly spaced, just because, right, if we plug in different values, like, so here's what has to happen for them to be evenly spaced. So let's say we pick values. Let's say we pick values of z that are z star that are evenly spaced. So let's pick, and we got to pick between 0 and 1. So let's say we pick values of z star that are like 1/10, 2/10, 3/10, and 4/10, just for example. Then we're going to get radii that are the square root of 1/8 natural log of 10. Right, because natural log of 1, sorry, I erased what my radius was. My radius is 1/8 natural log of 1 over z star. So you get 1/8 natural log of 10, square root of that. And then our next radius is going to be the square root of 1/8 natural log of the reciprocal of 2 over 10 is 10 over 2, so natural log of 5. And then the next one's going to be the square root of 1/8 natural log of 10/3, and then the next one's going to be the square root of 1/8 natural log of 10/4, which is 5/2. I'm pretty sure those are not numbers that all have equal spacing between them. We can use a calculator to check, but I don't think we really need to. Yeah, they're pretty. Yeah, I'd be willing to bet a lot of money without checking it. They might still look pretty evenly spaced though, because there's not, like, these aren't big numbers we're dealing with, so they could look pretty evenly spaced even if they're not actually evenly spaced. All right, let us talk more about directional derivatives. So I'm going to remind you guys of the formula you talked about in class today, and I will try to write it the way he likes to write it, which is the following, which is a perfectly fine way of writing it. He is writing that, so yeah, he used a couple of interesting notations. So he was either saying del f del S, which is not notation I'm probably going to use very much, or, and that's at the point, comma, at the point x naught, y naught. And you can also write it as d, he was using a v f, the directional derivative of f in the direction of v, at the point x naught, y naught. Either way you slice it, that's going to equal the gradient of f, which I usually write with an arrow over it because it is a vector, but he was not. It's okay if you don't write with the arrow. At the point x naught, y naught, dotted with the unit vector in the direction we're interested in, which is the vector v divided by its own magnitude. Great. So let's do some examples, and then we'll talk about a few kind of interesting pieces of information. So let's look, he did that example already in class. Let's not do that one. So let's do some fun examples. Let's say I want to find, so I want to find the derivative of this function f of xy equal to 5xy squared minus 4x squared y at the point 1, 2 in the direction. I'm going to make it a little less easy. V equal to 5, 12. Also, it seems like he's kind of all over the place with his vector notation. I typically like to write them as columns, but I do not think he does, so I will start writing them more like this, or even as with parentheses, which I know is not ideal, but let me do a thing here. I feel like my screen's a little dark. So that's maybe better. Let me know if the green pen is hard to see. Let me know. I will definitely use other pens. Okay, so we need to find the gradient. So the gradient of f anywhere is just the partial derivatives, right? It's the partial with respect to x, the partial with respect to y, as the components of your vector. So the partial with respect to x is going to be 5y squared minus 8xy. The partial with respect to y is going to be 10xy minus 4x squared. So that's your gradient anywhere. And then your gradient specifically evaluated at the point we were talking about, 1, 2, is going to equal, I'm just going to plug in 1 for x and 2 for y. So I'm going to get the vector, let's see if x is 1 and y is 2. I'm going to get 5 times 4 minus 8 times 1 times 2. It's going to be 20 minus 16, which is 4. And if I plug in 1 for x and 2 for y, I get 10 times 1 times 2, which is 20, minus 4 is 16. Great. I feel like I'm looking at, oh no. Sorry, I'm looking at someone else's notes on this, and I think they made a mistake. That's all right. I was like, that seems wrong. Yeah, that's definitely wrong. It's fine. Yeah, they really did. Huh, interesting. Okay. Anyway, sorry about that. So that's the gradient. Then if I want to find the directional derivative, I'm going to take that gradient, and let's do it in red. Directional derivative is going to equal, and so I guess I should use more appropriate notation here. My directional derivative is going to equal the gradient evaluated at the point 1, 2, dotted with the vector v divided by its magnitude. We just found this, right? This is going to be the vector 4, 16. The vector v divided by its magnitude, let's see, the vector v is 5, 12. The magnitude of v is the square root of 5 squared plus 12 squared, which is the square root of 25 plus 144, which is 169, the square root is 13. So that's going to be the vector 5, 12 divided by 13. Whereas I would probably write it, and it probably is easier to use the row notation instead of the column notation. Let's write it as 416 dotted with 1/13 times the vector 5, 12. Okay, so now it's just multiplying some components together. We're going to get 4 times 5 plus 16 times 12 divided by 13. That's going to be some ugly number. Let's see, 16 times 12 is 100 and something. What, 16 times 12 is 160 plus 30 is 192. So you get 20 plus 192, which is 212 divided by 13. So that tells us that at that point on your surface, in this direction, the steepness of the surface is a slope of 212/13, meaning that if you move in this direction, 1 unit in that direction, you're going to go up 212/13 of a unit. I will say, I do think the biological examples he's doing in class, the one example, like where he's talking about units, like I think he was talking about hertz per millimeter, it does give it a little bit more meaning, right? When you're talking about, oh, I'm talking about the rate of change of the outputs versus the inputs. So it's good to pay attention to that. Kind of like, oh yeah, we were talking about if you change a little bit of your input, how much change in your output is there? That's what's happening here. Let's look at some more examples. Actually, before I look at more examples, Sorry, one sec. Let's look at one more example. So let's find the directional derivative of, what have we got here? F of x, y equal to 1 plus 2x squared of y at the point 3, 4 in the direction of yes, but I want that, sure. V equal to, I don't want it to be so easy. But fine, we'll make this one easy, we'll make the next one hard. 4, -3. Okay, so same calculation. We have to find the gradient. The gradient is going to be, so let's see, if I take the partial with respect to x, I'm going to get 2 times the square root of y, right? Because you get the derivative of 1 is 0, 2x root y is just 2x root y. Take the derivative with respect to y, I'm going to get 0 plus, let's see, now I get 2x times the derivative of the square root of y is 1/2 y to the -1/2. Simplifying this just a tiny bit, it's 2 square root of y, and then here the 2's cancel, and you get x divided by the square root of y. Okay. So then, if I want to find the gradient at my point, I'm just going to plug in the point 3, 4, and get, let's see, if I plug in 4 for y, I get 2 times the square root of 4. If I plug in 3 for x and 4 for y, I get 3 divided by the square root of 4. So it looks like my gradient here is 4, and then this is going to be 3/2. All right. My unit vector in the direction of v. So what I often like to do is I'm going to say take v and divide it by its own magnitude. So v divided by its own magnitude is the vector 4, -3. I think we've seen this kind of setup enough times to realize, oh, the magnitude of that vector is going to be 5. Right, the square root of 4 squared plus -3 squared is exactly the square root of 25, which is 5. So, taking it all together, we can see that my directional derivative evaluated at the point 3, 4 in the direction of v, which is, this vector here, is going to be, let's see, this vector for 3/2 dotted with this vector, 1/5 times the vector for -3. And then we dot them together, 4 times 4 is 16. 3/2 times -3 is -9/2. And then all times 1/5. And then we could simplify that a bit if we wanted to, right? 16 is 32 tenths. 32 tenths minus 9, sorry, 32 halves minus 9 halves is 23 halves times 1/5 is 23 tenths. So what it's telling us is the slope, the rate of change of the function in this direction is 23 tenths output units versus 1. So if you move 1 in the direction of v, your function is going to increase at a rate of 23 tenths. Let's ask a slightly different question that's still related to this. What if instead of saying I want to move in the direction of that vector, I instead said I want to move in the direction of the point, let's say, I'm going to make something up that's not going to be particularly nice. Let's say the point, six comma, let's be annoying, yeah, 6, 5 halves. Sure. Let's say we want to move in the direction of that point. Well, we don't actually have the direction yet. I'm going to erase some of this. Our grading is not going to change, right? We're still taking the grading at that point is still the same thing. Yeah. Well, yeah. But our vector v is no longer 4, -3, right? So if we're starting at the point, let's draw a little bit of the picture. We're starting at the point 3, 4, and we're going in the direction of the point 6, 5 halves. There. This is our new direction vector. And so to find that vector v, we have to do these points minus those points. So the vector v is going to be 6 minus 3 for the x coordinate, and 5 halves minus 4, which is 5 halves minus 8 halves, which is -3 halves for the second coordinate. And now we want to find the magnitude of this. Now here's a nice trick. I want everyone to pay attention to this because it's actually really nice. You can find the magnitude of this, right? The magnitude of v would be the square root of 3 squared plus -3 halves squared. You get some terrible number that has a fraction, and then this would have a fraction, you divide the whole thing. But here's the thing. We're trying to find the unit vector in this direction. So, right, this is definitely longer than 1. So let's say there's my unit vector. Right, there's my unit vector here. And we got the unit vector by taking our vector that's going in that direction, right? It's going over 3 and down 3 halves, and dividing by its magnitude. But here's the thing. You can take any vector in that direction and divide it by its own magnitude and still get the same unit vector. So for example, if I doubled the length of this vector, oh, well, the vector that's double the length, we can call it W. No pun intended there, but double is double. Well, it's not V, it's W. Oh. In French, it's W, right? Then we work, right? Okay, anyway. Double V, not W. Okay, anyway. So we double this. The coordinates of the vector are now 6, -3. And that vector, where you go over 6 and down 3, is still in the same direction. It's going over 3 and down 3 halves. And if you divide this vector by its magnitude, you'll get the same unit vector. And what's nice about this? You don't have to deal with any fractions anymore. So if you ever have to find the unit vector in the same direction as a vector and you've got ugly fractions, you can say, I don't want to deal with the fractions. I'm going to get rid of the denominators by multiplying whatever that is, and then take the unit vector of that, and it's the same. So W divided by its magnitude is going to be this vector 6, -3, divided by the magnitude. The magnitude is going to be the square root of 36 plus 9, which is the square root of 45. And that seems much nicer. So yeah, I want to say that again. Whenever you're trying to normalize a vector, if the vector you're trying to normalize is kind of ugly and has fractions in it, just multiply by whatever you want and then normalize that. Here, my directional derivative at the point 3, 4 is equal to my gradient evaluated at 3, 4, dotted with the vector we just found. 1 over the square root of 45, 6, -3. Okay, and this gradient was the vector 4, 3/2. So we get 4, 3/2, dotted with 1 over root 45 times 6, -3. So that's 4 times 6, which is going to be 24. 3/2 times -3, which is -9/2, divided by the square root of 45. Which is not nice, but such is life. And if you want to simplify that just a little bit, 24 becomes 48/2, and 48 minus 9 is 39/2 over root 45, or 39 over 2 root 45. Okay. Some time is it? Okay, we got some time. I always help someone with a problem today where their direction vector was like super duper ugly. Like they got some direction vector that was like, I'm gonna make up something slightly like, it was maybe like, I don't know, 5 over 37 and 11 over 37. And they had to normalize that. Well, instead of normalizing V, we can normalize any multiple of V, specifically 37 times that. If you multiply that by 37, 37V is equal to just the vector 511. And then normalizing that, well, the magnitude of 37V is the square root of 5 squared plus 11 squared. Which I'm not saying is nice, but it's certainly nicer than dealing with 5 over 37 squared plus 5 plus 11 over 37 squared. So then that's going to be the square root of 25 plus 121, which is 146. So here's the thing. The unit vector in this direction is, in fact, 1 over the square root of 146 times that vector 511. You could also do it using this, right? It would be 1 over some terrible square root of 5 over 37 squared plus 11 over 37 squared times the vector 5 over 37, 11 over 37. I will tell you, if you do this calculation, let's just do it. I'll do it real quick. Here's what happens. You get 1 over the square root of, well, here you get 5 squared over 37 squared plus 11 squared over 37 squared, which becomes 5 squared plus 11 squared, which is 146, over 37 squared. And the square root of 37 squared is 37. And then you get 5 37s and 11 37s. And look, if you flip and multiply, the 37s are going to cancel out. And you get exactly nothing there. So what I'm trying to say, I know I said maybe a little too much about this, is make your life easy. If you have to normalize something terrible, make the thing you're normalizing less terrible and normalize that. Okay. Some things to know about the gradient. Where did that example go? We have more examples of this. Fine then. Sorry, 1 second. There we go. Sure. So let's answer this question. Let's ask this question. What is the maximum rate of change of the function 3xy minus y squared, sorry, 3xy minus x squared at the point -1, 1, and in what direction does it occur? Okay, so it's really easy to calculate this once you know what you're doing. So remind everybody, the gradient's a dot product. So, sorry, not the gradient, the directional derivative is dot product, apologies. Directional derivative is equal to the gradient of f evaluated at the point. I told you I should write, okay, fine. Sorry, to make it a little bit more precise. Directional derivative at the point x naught, y naught is the gradient of f evaluated at x naught, y naught, dotted with the vector v divided by its own magnitude. Okay. But there's another way of calculating a dot product, right? So we've been doing the dot product thing where you do, the x part times the x part plus the y part times the y part. But remember when we did dot products way back when? And we're like, oh, you can do the dot product by doing the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between them. I'm going to ask you guys some questions and I want some responses. So, first question. What is the magnitude of this vector v divided by its own magnitude? What kind of vector is that? What kind of magnitude does it have?
It'll have a magnitude of 1 since it's a unit vector.
Exactly. So this is going to have a magnitude of 1. So all we're getting, I'm going to write this is without the x naught, y naught part, is we're getting the magnitude of the gradient of f times cosine of theta. Okay, well, the answer to this question is the same as the answer to the previous question. What's the biggest cosine of theta can be? Also 1. Right. So the biggest this can be is when cosine of theta is equal to 1. This is going to be always less than or equal to the magnitude of the gradient of f, which means the maximum value this can have is actually the magnitude of the gradient of f. So before we get too far along here, the maximum rate of change is in fact the magnitude of the gradient of f. No ifs, ands, or buts about it. If someone asks you what's the maximum rate of change, you're like, oh, it's the gradient of f, the magnitude of the gradient of f. If they ask you what the minimum rate of change is, it's actually the negative of that, because if you change the direction you're going in, right? If the gradient is like I always call it the direction of steepest ascent, like, oh, it's really steep that way. If I turn around, that's the direction of steepest descent, which is going to be your minimum value. So if anyone asks you for a minimum value, take the gradient and go in the opposite direction. You'll get the opposite value. Okay. The other question we want to answer is, what direction is this in? Well, for this to be a maximum, we say cosine theta has to equal 1. And what's the angle when cosine of theta equals 1? Is it 20 degrees? Is it 90 degrees? Is it 180 degrees? It's none of those. The angle is 0 degrees. meaning, well, the angle is supposed to be the angle between your two vectors, your gradient of f and your direction vector. But if the angle between the two vectors is 0, that means the two vectors are in the same direction. So that means that the direction vector v is in the direction of the gradient of f, which means that the direction that the maximum rate of change occurs at is the direction of the gradient, which is going to be the gradient divided by its own magnitude. So long story short, you don't have to figure this out every time you're trying to answer these questions. If someone says, what's the maximum rate of change? We're going to find the gradient and take its magnitude. Let's do that. So the gradient of this let's just find the gradient and then plug in the 0.11. So the gradient is going to be the partial with respect to x, which will be 3y minus 2x. And then the partial with respect to y is going to be 3x. And if we plug in that point, the gradient at the point -1, 1 is going to be, let's see, -3 minus 2 is -5, and this will be -3. The magnitude of the gradient is going to equal the square root of -5 squared plus -3 squared. That's going to be the square root of 34. So this function, at this point, the maximum rate of change is the square root of 34. The square root of 34 output units versus input units. So, right. So if we were talking about, like his example, hertz per millimeter, if you're at that point, the maximum rate of change is square root of 34 hertz per 1 millimeter. Not that there's any reason for that. It's numbers. It's just what I remember from class there. The direction is also not terrible. In fact, we already have all the things we need for the direction. There's the gradient. There's its magnitude. The direction is going to be 1 over root 34 times the vector -5, -3. That's it. And I did make one tiny error. You guys didn't catch it. Let me get away with it. It's okay. I know I go fast. And you guys are like, oh, maybe you said this actually should have been a +5. Right? If I plug in 1 for y and -1 for x, I should get 3 minus -2. So that should actually have been a +5, which doesn't change our magnitude, fortunately, but does change this answer. Sorry about that. What else do I want to say here? Sure, yeah. So the last thing he said in class today was that the gradient is tangent to the level of curves, which is true. So the idea is, and so I would really encourage all of you to think about these gradients, all the stuff we've been talking about lately, in the context of contour maps being like actual maps, right? Like actual contour maps. Meaning you're looking at, you're like, oh, the mountain's this high or this high, this high. And here's the thing about the gradient. So let me just draw like, I had a picture here. Let me see. Stuff keeps disappearing. There we go. So let's say we had kind of this, let's say we had this contour map. We have something that looks vaguely like this. And then it's going to be kind of a little bit saucy on the inside. And then a little bit more like that and like that. And let's say this is 100 feet high, 200 feet, 300 feet, 400 feet. Okay. So here's the deal. Gradient is at any point, is the direction that is going to get you up the mountain the fastest. It's the direction of steepest ascent. So for example, if I'm starting, say, like right here, my picture is not excellent, by the way. I'm starting right here, yeah, of course. Yeah. Maybe let's start right here instead. I'm starting like right here. I'm going to be going that way. Right, that's my gradient. It's going to be getting me up the mountain the fastest. And importantly, my gradient is perpendicular to my level curves. It's true. And the thing is that if the gradient is perpendicular to the level curves, well, the tangent line will be perpendicular to the gradient for the same reason. And so what people often ask us to do is find, actually, I feel like I should give more reason for that. So let's say at this point, right, let's say we're here, and instead of moving in the direction of the gradient, we want to move along this tangent line, right? So if you move along the level curve, what happens to your elevation? If I'm on this curve the whole time, the elevation doesn't change. So this is my direction vector v. I want to find the directional derivative in the direction of v of this function f. Well, I already know the directional derivative is 0, right? I'm not changing my elevation. There's no change in the function value. My derivative is 0. But I know how to calculate the derivative. It's the magnitude of the gradient times the magnitude of the vector v times cosine of the angle between them. The gradient is not 0. This unit vector is, or I should say, the gradient doesn't have a magnitude of 0. This unit vector does not have a magnitude of 0. So cosine has to equal 0. Which means the angle between them has to be 90 degrees. So that's why the gradient and the line and the tangent line to a level curve are perpendicular, because they have to be. Yeah. So sometimes someone might ask, and I know we're almost out of time here. Someone could ask a question like the following. Here's a function. F of xy is x times y. And we want to find the equation of the line tangent to, what have I got here? The level curve f of xy equal to 6. So here's the idea. We've got, yeah. Oh, sorry. At the point 3, 2. Here's what we've got. We've got this graph. We've got 6 equal to xy. We could solve for y. 6 over x. It looks something like this. And at the point 3, 2, maybe we're right here. I want to find the equation of that tangent line. Well, could I do it the normal way and be like, okay, I can totally find, the derivative of that, take the tangent line? Sure. But we could also say, hey, look, I know the gradient is perpendicular to my tangent line. So I can find the gradient, which I totally can. The gradient of this is partial with respect to x is y, partial with respect to y is x. And at the point 3, 2, my gradient is going to be the vector 2, 3. And the slope of that is over 2 and up 3. So the slope of the gradient vector is 2/3. And if you're perpendicular to that, the slope of our line is the negative reciprocal, -3/2. Which, yes, we totally could have found if we taken the derivative. We didn't have to. We fixed the derivative. Okay. So you can totally find the equation of this line by saying, okay, it's going to be y minus 2 equals -3/2 times x minus 3. So you can also use the gradient to find the slope of a tangent line. We're out of time. Last thing I want to say, oh, does that say slope of our line? Yes, and about the worst handwriting that you can see on the board. Yeah, this says the slope of the gradient vector is 2/3, and this says the slope of our line equals -3/2. And I know it looks awful. I'm sorry. Last thing I want to say, the two big things to take away from this are, well, maybe the three things: how to calculate the directional derivative. It's the gradient evaluated at your point, dotted with the unit vector in the direction you want. I will also say, quick aside, if you're given a vector, you're just finding the direction of the vector. But if you're given another point, you have to find the vector between your point and the point you're ending up on. So if they give you a point, don't just be like, oh, that's my vector. It's not. But the two other things I want to say is the direction of steepest descent, or the direction of the maximum rate of change of a function of two variables, is the direction of the gradient, which I've erased. And the maximum rate of change of a function of two variables, or the maximum ascent, that's not really the maximum rate of ascent. I don't know. The maximum rate of change of a function of two variables is the magnitude of the gradient. So those two things, remember those things, they're going to come up.